All right, so on Friday we were taking a look at how we can figure out the area trapped between two curves, and we realized through a little investigation that if we simply take the area from the top function graphically and find the area of the bottom function graphically, we can subtract those two areas to figure out the area that's trapped. So very similar to the first fundamental theorem of calculus, we have, again, this kind of top minus bottom idea, but now it's just related to the functions when we're looking at a graph. Okay, so top function minus bottom function. We're going to practice this a little bit more today with this slightly more complicated example, because now we have two regions we're going to analyze, region R and region S. And then we're going to take a look at the insert I want you to add in after your notes that I passed out. We're going to take a look at how we can measure area to the x-axis, but also to the y-axis. Sometimes measuring it to the y-axis is going to be much easier and less complicated than measuring it to the y-axis. So we're going to do a little investigation so you can clearly see when that might be a little bit more appropriate. But first we're going to start on page 448. So to the right we have the functions a half plus sine pi of x, and then the exponential 4 to the negative x. Let's first start by identifying the intersection points, because if you were to take a look at the picture on your notes or in your notes on your paper, those intersection points are pretty important because that's where particularly region S begins and ends. So knowing those intersection points is going to help us set up our integral in terms of our bounds. So this is why we need our calculator today. We're going to go ahead and graph these functions and figure out their intersection points. Make sure you're in radian mode because we're dealing with trig. They don't really give us any numbers on the x or y axis to help us get a window for our calculator, so it's up to us to figure out the window we should use. After you type in your functions, let's go ahead and change our window. So I'm going from -2 on the x-axis to 4. Maybe I'll just change that to 5. I really don't know. We just need some beginning window to start with, and then we'll go ahead and change it if we have to. So I'll go from -2 to 5 for the x-axis and the y-axis. All right. Clearly, that's a little too much, because notice how we're only really looking at this first, I guess, hump in the wave. So we can cut down this window a little bit so we can just focus on that portion. So let's make our window perhaps go from 0 to 2 for the x-axis, and then maybe we'll go from -1 to 2 on the y. Okay, we'll trim it down a little bit. We can always go back and change it if we have to. I'd say that's pretty good. We can just ignore a little bit more to the right here, but at least we can clearly see those intersection points that we're trying to calculate. Do we remember how to figure out intersection points? We did it a little bit on Friday. Do you remember what buttons to press? Second trace, okay. And then intersect is number 5. We're going to go ahead and move the cursor to where we think it is, so it just depends on which one you want to find first. This one's pretty close to 1 already, so maybe I'll just keep it there. And you're going to hit enter 3 times. All right, so we get intersection of 1, comma, 1/4. Let's go ahead and repeat the process. and we'll try the other one. So second trace, intersect is 5, move the cursor. All right, and we'll write down the other one. Let's perhaps round these to maybe 4 decimal places. I know this year we've been rounding to 3, but we really should only be rounding our final answer to 3 decimal places. So that means if you have to use any other numbers in your calculation, those should be more than 3. That way you're a little bit more accurate. Does that make sense? Do we understand that? So we're only going to be rounding our final answers to 3. So we'll write down the intersection as 1.782, comma, 0.7811. Are we okay with finding a intersection point on the calculator? So far so good? Okay. Let's also perhaps label which function is which on our paper. Okay, so after we graphed it, that might have been helpful for us. We saw the wavy type shape was the sine function. So that was the f of x one written in the directions. And then the decreasing function was the exponential g of x. All right. So let's see if we can tackle the first area. We're going to try to find the area of region R. We're going to go ahead and think about if we were to draw in vertical rectangles. I know it's a very small region, but if you were to draw in some vertical lines, where would those vertical lines begin? Where would those vertical lines end? Okay, those are the bounds on the integral we need. And then we also have to figure out what function does the top of the rectangle touch, what function does the bottom of the rectangle touch. We'll use the top minus bottom function rule to help us with that area between the 2 curves. So let's perhaps start with the bounds. If you were to draw in those rectangles, where do they begin and where do they end? Just for region R. There we go. We're going to have to utilize that intersection point we found, specifically the x-coordinate, 0.1782. Okay, and then for the functions, utilizing those rectangles again, the top of the rectangle is touching the exponential curve. That was the g of x function. And then we're going to subtract the bottom function, which was f of x. Now we got to be careful because f of x has multiple terms in it. If we're subtracting that function, we're subtracting every single term. So everything should switch a sign. Okay, top function minus bottom function. From there it's going to be some calculator work. So go ahead and take the time to type it in and we'll find the region or area of region R. I got 0.065. Sound good? We ready to go on to S? Okay, we're going to kind of repeat the process, but just for a different chunk or section of the graph. So let's take a look at region S. If we were to draw in some rectangles throughout that region, where do those rectangles begin? Where do they end? Can we figure out the bounds for our integral? To 1. Good. Those are the intersection points. Perfect. All right. And then when we look at those rectangles again, what function does the top of the rectangle touch? What function does the bottom of the rectangle touch? So for region S, the top function is that trig function. And the bottom function is always the exponential. So notice how it kind of did a switcheroo from region R. All right, calculator work from there. Point 41. Good. All right, we starting to feel comfortable with these? Okay, it's all about finding the bounds, sometimes those intersection points, and then the top function and the bottom function. Let's try this last one. Find the area of the unshaded region bounded by the graphs and the x-axis. Okay, so the unshaded region and the x-axis. That's kind of all of this white stuff down here. So this one might be a little bit tricky. I mean, they don't really label it R or S, so we got to figure out what are they talking about. But let's try to approach this one. We did region R and region S. If we were to throw in some rectangles, let's think about kind of what those rectangles are touching as we draw them through the graph. Do you notice anything interesting about these red rectangles that I drew compared to the other ones we did for R and S? Do you notice anything as you drew them?
Some parts.
Uh-huh.
They touch both functions at the time.
They touch both functions. So these first ones you draw, notice how they touch the trig function, that was the wave. But after a certain point, they changed and they started to touch the exponential. And then again, after a certain point, the last few would be touching the trig function again. Do you see how it changed as you go through that specific region? We didn't really have that happening for R and S, because for maybe perhaps S, as we draw the rectangles through, the top is always the trig function and the bottom was always the exponential. Okay, it was very consistent all the way through that region. But for this one, it's not. So we have to be careful on how we set up our integrals because we're having some change going on as we go through. So let's see if we can calculate this. These first few rectangles we draw, the top function is the trig, and the bottom function is the x-axis. So we don't really have another function to subtract. The area is being measured to the x-axis anyway. So for the first few rectangles we draw, they begin at 0, and it's not until you get to the intersection point where you change the function that the rectangles were touching. So our upper bound is going to have to be that intersection point where that change occurs. So from 0 to that intersection point, you're essentially calculating the area under the trig function to the x-axis. But that's just for the first few rectangles that you drew in, just as a visual. We certainly have more area to calculate, so we're going to have to use some more integrals. Okay, the next few rectangles that we draw, notice how they touch the exponential curve until you get to that second intersection point. So our bounds would be from the first intersection point to the second. And you're just calculating the area under the exponential curve because notice how it's being measured to the x-axis. We don't really have another function to subtract. But we still have a little bit more area, and it's in this kind of last little section on the right-hand side over here. The last little section goes from that intersection point, which we know happens at an x value of 1, and the area of the unshaded region ends when you get to the x-intercept of the trig function. Do we know what that is? No. Can we figure it out though? Definitely, because we have our calculator. So let's see if we can do that. So we'll go back to the graph. We're essentially trying to figure out the intersection point, the little lights there, the intersection point right there. So let's go ahead and use our calculator. We'll do second trace, and we'll do the 0 command for that x-intercept. And we'll move the cursor along the trig graph till we get there. It's going to ask us a few questions. It first wants us to choose a point on the left. So we'll go to the left a little bit and hit enter. Then it wants us to pick a point on the right. So we'll hit enter. You're basically telling the calculator the x-intercept is somewhere between those arrows. And we'll take a guess. So the x-intercept looks like it happens at 1.0804. That needs to be our upper bound because that's where the area ends. And in that last little section, you're calculating the area under the trig graph. So we'll have to go ahead and use that as our function. So this question isn't necessarily asking us for the area between two curves. It's asking us for the area to the x-axis in a certain region, but notice how the function changes in that region. So if the function changes, our integral has to change as well to account for that. So from there, it's just going to be some calculator work. So you could do one at a time and then add them up. You could take the time to just type it in exactly on your calculator all the way through. But in the end, these three separate integrals added together should give us the area of the unshaded region. So go ahead and take a second and check that. Yeah. All right, I got 0.5. 486. Sound good? Okay. Can we visually see and understand why we had to break up that region because of those rectangles? Okay, I know it might sound silly to draw in those lines, but it's going to be a good visual for us. Yeah?
Haven't you just done the integral of f of x from 0 to 1.084 minus the area, the integral, minus what you get for s?
So you want to tackle this a different way. So you want to do the area of the whole parabola, the whole trig function minus the area of s.
Yeah.
That would have worked as well. Did you get the same answer?
Yeah.
Perfect. There's more than one way to do something. Okay. The reason, though, I wanted to approach it this way is because when we go over area to the y-axis next, we're going to have to break it up. But that is another way to approach it. Okay. So either way, we should get the same thing. Do we see what Justin wanted to do, though? He took the area under the trig graph, bless you, which would have been everything to the y-axis, and then he just subtracted region S. That would give you the little leftover piece. Okay, so more than one way to do something. Really good. Bless you. All right, let's go ahead and take a look at kind of x-axis area versus y-axis area. This is when drawing those rectangles might be a little bit more appropriate, or for a good visual for us to see what's actually going on here. And measuring area to the y-axis sometimes might be a little bit more beneficial. And I'm hoping this example kind of helps you to see or understand that. So we're going to take a look at the same graph in the same area two separate ways. We're going to try to figure out, I'm going to erase it in a second, but we're going to try to figure out this enclosed area. We're going to try to do it measuring to the x-axis, meaning vertical rectangles, or to the y-axis, meaning horizontal ones. Okay, we're just switching the way that we measure the area. Let's try to tackle this one the same way we were doing all of the other ones, okay, to the x-axis. We have three different functions. We have the positive square root, the negative square root, and then the linear. Okay, and I tried to draw in the intersection points so we could see them pretty clearly. This intersection point is at 1. And then this other intersection point is at 4, okay, on the x-axis. If you were to draw in your vertical rectangles, okay, start off with a few and work your way through. Do you notice anything about those rectangles as you draw them through the region? Are they always touching the same functions? That's mainly what we need to notice. Or is there a change? What do you think? Let's see, the first few you draw, the top function is the positive square root, the bottom function is the negative square root. The later ones you draw, the top function is the positive square root, and the bottom function is the linear. So clearly there was a change. We have to figure out where does that change happen and take that into consideration when we have to write our integrals. So if there's a change, we're going to have multiple integrals to account for each separate section. So let's just start with the first few rectangles. Okay. It looks like the change happens at that first intersection point. So the first few rectangles would go from 0 to 1. Those first few rectangles, the top function was the positive square root. And then we have to subtract the bottom function, which was a negative square root, but if you subtract a negative, that would change to a plus. We still have more area to calculate, though. All right, so the last few rectangles you draw go from 1 to the last intersection point of 4. And in that little region, the top function is the positive square root, and the bottom function is the line. But if you're subtracting the line, you have to subtract every part of the line. So it would change to a minus x plus 2. Okay, so we can visually see the change in the rectangles as we draw them through the region. Go ahead and utilize your calculator to find the area. I got 4.5. Does that sound right? All right, so what I want to do is just take some notes on when we can use kind of an x-axis measurement, aka we're using a dx integral because that's what's written on the end. So if we want to go ahead and measure area to the x-axis, we have that idea of the top function minus the bottom function. If we're measuring area to the x-axis, that means we need x-axis bounds, aka the x-coordinates from those intersection points that we find. And if we're measuring area to the x-axis, notice how when we write the integrals, we have x variables inside that integral for our functions. So we have x variable functions. And we have a dx on the end. Can we think about how these x-axis properties might change if we now want to write an integral to help us measure the area to the y-axis? Can we think about what those three things would change to? Instead of doing top minus bottom, what do you think that might change to? Instead of top and bottom, we can change that to left and right. Good. So this would be actually right minus left. Notice how top is kind of a positive direction. Right is a positive direction. So this would be right minus left. Instead of using x-axis bounds, if we want to measure area to the y-axis, we need y-axis bounds. And in terms of our integral, we would need a y variable function and a dy on the end of our integral. So we're going to go ahead and practice trying to find the area to the y-axis. We're used to the x-axis. That's what we've been doing since we've introduced integrals. But now I hope you notice if we switch it, okay, it might be beneficial. So let's see how we can go about doing this. Okay, I'm going to move the page up a little bit. Instead of drawing in vertical rectangles, let's go ahead and draw in horizontals. I think we can do that. Let's go ahead and try to figure out the bounds of this area. So if we're measuring to the y-axis, we got to figure out those intersection points, but where they occur in terms of the y-axis. So it looks like visually the first intersection point is at -1, and the second intersection point happens at a y value of 2. Are we okay so far? You see how we're changing it up a bit? We also need to make sure that we have y variables in our integral. So with the equations at the top, notice how we start off with y equals something. Okay, we might have to switch those around as well because we're measuring the area to a different axis. So we're going to go ahead and switch the equations. That means we got to figure out what these would look like in terms of x equals. So let's think about the first one. How can you get the x all by itself for the plus or minus square root? How can you get rid of a square root? We'd square it, right? So the first one would change to x equals y squared. And then for the second one, if we tried to get x all by itself, we would simply just add the 2 over. So x would equal y plus 2. So take a look at what happened here. The positive and negative square root now changed to a single function. It's just y squared. Doesn't it kind of look like a parabola just on its side? Makes sense because it's squared. And then the linear is now y plus 2. Take a look at how you drew in your horizontal rectangles. Do you ever have a change in function? These rectangles always touch the line on the right, and notice how they always touch the parabola on the left. There was no change in function like there was previously, right? When we did it for the x-axis. So if there's no change in function, that means one integral is all we have to use. Notice how we had to use 2 when we did the x-axis. So let's see what this single integral might look like. Okay, the bounds are now on the y-axis instead of the x-axis. So we would need -1 to 2. Now we need the right function minus the left function. We said the right function we changed to y plus 2. And the left function is always that parabola, y squared. And since we're measuring to the y-axis, we need that dy on the end. We're just changing the variable we're using. Now here's what's a little different. This is what the integral looks like on paper because we're measuring to the y-axis, but you can only type in the variable x on your calculator. So I don't want you to get them confused. I want you to type this in on your calculator just using x's instead of y's. But it should give us the area. Hopefully we still get 4.5 because it's the same region. Does it work out? Okay, so I just want you to be aware, okay, that there's more than one way to measure or find the area between two curves. It's just a personal preference. Do you feel like using multiple integrals, trying to find where those changes happen? Or maybe you can simply switch a few equations and just use one integral. Either way, it still is going to work out in the end, okay? But do we see the difference between the two, how you have options, okay? I just want you to be aware of that because there might be some questions in the homework that ask you about the y-axis area or how you can measure it. So just be aware that this is where it might be in your notes, okay, if you have to reference it. How are we doing with the area between two curves? We're doing okay? Top minus bottom, I think we're familiar with that. But if we're measuring to the y-axis, right minus left. Very similar concept. All right, yes?
So what's going on tomorrow because we have a blank spot there?
Tomorrow I might let you guys have a homework day, or I might give you extra practice because 8th period is having, or some of us have NHS induction, and I'm going to be missing all of my most of my 8th period tomorrow. So I don't want you guys to get too far off from the other class. So tomorrow will be kind of a homework or a practice day. Bless you, bless you.